take you through exponential decay modeling. Example here, radioactive substance is decreasing, so that's why it's decay, such that 2%, so 0.02 of it is lost every year. This is known as radioactive decay. Originally, there were 200 kilograms of this substance. So how much remains after 1 year? We could now just take our formula from the growth and switch the plus to a minus for decay. That's the only difference here. So present value, future value, rate, and time. So we plug in present value is 200 kilograms, and then 1 minus 0.02, and it's after 1 year, so the power here is just a 1. So we're just doing 200 times 0.98, which gives us the 196. Now, a question that comes up a lot with decay and radioactive substances is the half-life. So that would be, how long does it take for the initial value of 200 to go down to 100? And the way we have to do this is set up our equation, 1 minus 0.02 is 0.98, and leave the variable in there, and it's actually, we're solving this equation for t, which is pretty difficult at this point. And what we're going to do is sort of guess and check. And also we could use a graphing calculator. So after about 34 years, so if we plug in 34 here, we get just about 0.5. Not exactly, because it's actually happens somewhere between the 34th and 35th year. So this is just kind of a guess and check way to do this. You'd have to plug in powers and check. Or you could use a table, which we'll do in another example. So if the population of a town is decreasing by 4% per year, started 12,500, which of the following is the projected population in 10 years? So plug everything into our formula. This is the present value, 1 minus r to the t, and this is the future value. So how do we get this? We do 1 minus 0.04 is 0.96. Do 0.96 to the 10th power first, and you get about 0.6648. And again, leave all these decimals here because we can't round this yet. If we do, our answer is going to be way off. So then we multiply that by 12,500, and we get 8310.407, which is why I rounded to 41. And then again, this is population, so really we can take away that. Let's just say 8,310 people. So that's what option here. Okay, number 3. Hydrologists have found the amount of water that a soil can absorb in inches per hour decreases by 30%. So that's 0.30 or 0.3. And a particular dry soil is initially able to absorb 4 inches of water per hour. So that's the present value. So which equation can we use to model this? That's going to be this first one, because our initial value is 4, and then we do 1 minus 0.3, which is the 0.7, and then we raise the power. These two, this one, actually, they added 1 plus 0.3, so that's going to be growth, but it says it decreases, so that's why we did the minus. And these just have the numbers kind of backwards. They're raising 4 to the power, which is, you don't take the present value and raise it to the power. So now that we have an equation, we can answer this question. A steady rainfall of 0.5 inches per hour is flooding this soil. Water will run off this soil when the rainfall rate exceeds the rate at which the soil can absorb the rain. At what time will the runoff start? So we have to sort through and figure out. Usually the problems you're trying to solve here is when you take your model and you set it equal to whatever number is given. So, and we need to solve this equation, kind of like the one I did in one of the first examples. And so here we're going to actually plug in this into a calculator or Desmos. 4 times 0.7 to the power, and you can call it x on your calculator, and then see guess and check number of years. When is this going to equal 0.5? And so when I plug this into my calculator, I get an XY table. After 1 year, it's equal to 2.8. After 2 years, 1.96, and so on. And so at some point between the 5th and 6th year, or 5th and 6th hour, it goes from 0.67 to 0.47. So the value of 0.5 was somewhere in between there. So we could say between 5 and 6 hours, or somewhere in between the 5th and 6th hour. Eventually, we'll learn how to solve these equations exactly and find the exact value, but we would need something called a logarithm in order to do that.